Welcome guys. This talk will give you direction of our lab. So this will be probably we will not arrive the contents of this talk in 2 years. So probably it will take about 2 years to for us actually work on this. We are doing the first phase of our work. So the national lab here is to give you guys about what our lab is working on now. So I just say, oh, do this, you do this, and things like that. So now it's a good time for us to sit around and understand the national lab behind our work. And it requires some background. So it requires actually lots of background. So, however, my plan here is I will probably do it like 2 or 3 hours long. So this will be just the first session, and next week I will continue. So take your time, don't hurry, and try to understand the content right now here. Do not go home and I'll study this, things like that. And luckily for you guys, my talk is actually very easy. So there is no mathematical background that is difficult here. So if you try, you can understand it. So let's start. So if we compare machines and humans, I am mostly interested in the things that are easy for human, however very difficult for machines, right? This is where I am very interested. And things like that is like nowadays when you see Amazon, there are 10,000 reviews, and there are questions like this: why customers buy? What are problems? What are my alternative or competitors? And more important nowadays, can I trust this review? Things like that. So, however, what is interesting about this kind of task is, if I ask Sanjay to answer why customers buy, then his answer and my answer will be totally different, right? However, his answer is also right and my answer is also right. There is no right or wrong here. We call this kind of task as open-ended tasks. And a good example of the open-ended task is, do you know image capture model? So given an image, there are neural net model that generates a textual description, right? And let's say if I ask Sanjay, if I give him a picture and please describe it, and I describe it, then his version and my version will be totally different. And if I ask 10 people, their version will be all different. However, and let's say if we ask a model to do this, then a model will generate some version. And the problem here is, if I see the machine's version, we know immediately, oh, this is right, oh, this is wrong. It's very easy for us, right? However, developing an algorithm to evaluate this textual description is actually very difficult, right? There are no fixed set of ground truth data. It is open-ended, right? The answer is set of the answers, right? Answers are open, so there is no boundary. So this creates lots of problems for the so-called things like machine learning. So if you have taken the machine learning course, the basic loop is that there is input and machine generates an output, and we evaluate the machine's output using algorithm and do it slightly better, right? We see if the score gets better and better and better, things like that. That is our basic loop. However, because we cannot do the evaluation automatically, it creates a lots of problems. So we call this kind of problems open-ended tasks. And open-ended test is like, can you read this cartoon? Can you still read the text here?
Yeah.
Yeah, so this is supposed to be funny, but it shows that open-ended task deals with the unstructured data. Unstructured data is like natural language text or image, photo, like things like that. Those are unstructured data. What is a structured data? Structured data is like SQL database. So you see the difference. And open, as I said before, open-ended tests can generate lots of different but justifiable answers. So this one is also supposed to be fun. I'm not sure if you guys can still read this. It's a little small. Can you read it, Sanas? No?
I'm blank.
Okay, yeah. You can come closer if you want, yeah. The goal over here is understanding things. So, Sanjay, you can read this, right?
Yeah.
Yeah. So, and most challengingly, open-ended tests requires world knowledge. So, knowledge about the world. So, this is one challenge with open-ended task that is very difficult. What it actually means is that the information required to solve this task is not inside the question. You should have outside information, and actually the world knowledge and the open-ended task is two different things. As I said, open-ended task is very difficult for test automatically. So if you do some algorithm that does the open-ended task, it's very difficult to test. So computer science people, this is by the way just additional information. Computer science people hate this kind of problem because it's difficult to score, right? So it will be great if there is some problem that still requires knowledge about the world, but it is very easy to evaluate, right? So this is a slightly different problem. I am interested in the so one of them that is very popular nowadays is things called Winograd schema challenge. So let's start with the first one here. Can you read this? The city councilman refused the demonstrators. Can you read this?
Yeah.
Let's say if the word here is a field, right? Then who are they? My question is, can Saros answer this? The city councilman.
Yeah, which one?
Who is they here? The councilman or the demonstrators?
Demonstrators.
Demonstrators.
No,
Councilman. Councilor.
Yeah, councilman.
Councilman.
Yeah.
Saros, do you agree?
Yeah, councilman.
What happens if the word here is advocated? It becomes a demonstrator, right? Maybe it was slightly difficult because of the language required is heavier. So let's see if there is another example. Okay, this one is. So let's do another test. The trophy would not fit in the brown suitcase because it was too big. What was too big?
The trophy.
What if it was small? It was too small. Then what is too small?
The suitcase.
The suitcase, right? So let's see. It's to solve this problem. Do you guys remember that I talked about the three things like in the natural language processing? There are three main, how I say, approach. Three big approach. I think I told this already. Bhaskar, do you remember what is the three big approach?
Word embedding.
Word embedding is slightly lower, too much detail. Word embedding is actually one technique of some large scheme. How about anybody?
Phonetics.
Phonetics? No. So the first scheme here is a bag of words model. So it means we chop the word into things like is how companies like Google does business. So I eat fish eat meat. So in the bag of words model, you cut those and put in the bag. So those two sentences becomes the same. So this is the oldest approach. That is, however, still most of the industry applications are working on this principle. So that is the first thing. And do you guys remember the Jeopardy test? Jeopardy. Jeopardy. Do you guys know what is Jeopardy? You guys can type IBM Jeopardy. So Jeopardy is a quiz show that is a television show. So, and people, like three people sit here and I say, Napoleon was born in this city and things like that. And at some point when you know the answer, you put the buzzer and say the city is something like that. So, and IBM built a machine that defeated this task. And what they did was they searched for the internet or Wikipedia and search for the Napoleon and like a bone, and then they, let's say there is a city, let's say, for example, let's say this is Paris, and then they checked this hypothesis on the internet again. So they searched these three words, and let's say this was the first hypothesis, and the second hypothesis was because I don't know other French city, Napoleon born Berlin, and if you compare the search result of those two hypotheses, let's say if the Napoleon was born in Paris, there will be more documents containing this pair than the other pair, Napoleon born Berlin, right? This is how Jeopardy, IBM built a machine that could do this, right? And there is going this direction, there is the second approach here is, Pascal, do you remember? Any idea?
Remember removing words like the, is.
Oh no, it's one of the techniques on the bag-of-words model. So
Maybe cosines or not?
no, cosine similarity is
Again, bag-of-words.
a technique in the bag-of-words model. So almost everything you learn during your course, it belongs to this category. It's many tricks on this because you can do a lot using this trick. I can say almost everything Google does nowadays is belongs this category, and slightly advanced.
It's remembering the word, which word should
Yeah.
come.
Then can you say the basic intuition behind this?
It's like if you are if you have the sentence like so we find out, okay, if this thing can happen, so he is swimming, so swimming can happen inside the lake. More probability can be a lake, not a sea or kind. So he predict next should be the lake, or yeah.
Yeah.
Relation between words. So
Yeah,
how-
relation between words. So what you said is, I think probably you are confusing that with the language modeling. So language modeling is given so far this and predicting the probability of next word. So you might think this is very clever, but this one also belongs to the bag-of-words model because basically, let's say it is counting the occurrence of he is swimming in the, and then count the words that is following in the internet, right? If the most frequent word was a lake or pool, things like that, you can assign a probability. So bag-of-words model, you can do a lot, and the relationship between the word, right? Let's say in the blue lake. Then what you can see is there is a he, and what is he is doing action. Let's say this is action relation, and he is doing swim, and where. So where he is, where relation, and he is in the lake, and the lake has like a color relation, and it is a blue, right? So he might have a black, he might be white, he might be yellow, he might be Asian. So given this natural language sentence, you can construct knowledge database which composed of the three tuple. The tuple is this is actually graph, but the way you represent graph here is he and like action and swim, he location, and it's a lake, color, and it's blue. So we can say subject, relation, and object tuple. So you can extract this set from the natural language. So was like Barack Obama was born in let's say Washington D.C. in 1987, something like that. Then from that sentence, you can extract lots of knowledge tuple like that. So if we build a knowledge base from all contents in the internet, what will happen? So there will be lake, blue lake and white lake and salty lake. Salty is not color relationship. So let's say there is a 70% of the color relationship with the lake was blue, and 20% of the lake was white, right? Then you somehow build a knowledge about the world. In the world, lake if we ask about what color is the lake, we can say about 70% blue, 20% white, things like that. So you can know what is the color of the apple, color of the lemon, what is the color of school bus, things like that, using this knowledge base. That is the second approach. However, you cannot still solve the Winograd test here because let's go back to the Winograd test.
This model is called solution. What is this model called?
Knowledge base. And also search on the information extraction, OpenIE, things like that.
Google Knowledge Graph is built.
Yeah, Google Knowledge Graph is this. So, yeah, that is what many people are doing now in academia. Still, do you think if we have this knowledge database, do you guys think we can solve this problem? Aishwarya, why do you think you cannot solve this problem with this knowledge database?
Because the association is not clear. I mean, the context changes. The context is not captured of this. I feel.
Yeah.
I don't know how to explain it more clearly.
Yeah. If we search on the Google,
Yeah.
if we read all the text in the internet and see trophy and suitcase, and
They can be big, small, and shape, right?
oh yeah, they can be big, small.
All these terms are relative terms, like big is with respect to something. Like this bottle is smaller than this laptop.
Yeah.
Or the bottle is bigger than this.
Yeah. That's actually good observation. There are many reasons why the model, this knowledge base cannot solve this. Also, think about a person. Let's say he cannot see the world, he cannot touch the world, and he has just read all the text in the world, let's say. Then, do you think he can? It's a slightly different.
It's basically in a way like the lake, and lake has the adjective is a blue. So once we go for a lake, we can expect blue color associated with it and the white color associated with it. But it doesn't mean that all blue is a lake. So it is not reverse is true. And in this example is a reverse. We are talking about big or the small. So it is big, but we can't say the big is associated with the suitcase or the trophy because it can associate to anything. We are trying to go in a reverse direction in this example.
So then, how did you solve this problem?
So what I am doing right now, this model is not very good to solve this problem. We have to think about another thing. This model cannot apply directly.
Yeah. So
we to solve this problem, we need to go in a reverse direction. From the big, we need to go find out to which it is associated. So we are trying to go in a reverse. Where this model is not very helpful.
And we have a clue that it says would not fit in such kind of words helps us to determine.
Yeah, actually, that is a very good observation. So it's actually this word fit, right? That makes you, when you decide the big or small, and you think about the fit. And for fit, you know, to fit something in, the outside thing should be larger, and the inside things should be smaller, things like that. So this is like a state of the art. This is the challenge people are facing. Currently, no deep learning, whatever can solve this. So, you know, people say, oh, machine cannot win the Go human, right? Machine cannot draw, machine cannot do image classification. many things are already done by the algorithm, right? So people are saying, oh, machines, you still cannot do this, right? So this is one example that you need to memorize. It's called Winograd schema challenge. This is an important thing. So let's go back. So here is a open-ended, even though Winograd task is not open-ended. It has a ground truth value exactly. But Winograd task and open-ended task both requires word knowledge. So we human have no problem in doing this task. It's easy for human, but difficult for the machine. However, the problem with the human is difficult to scale up because there are lots of data, and if I ask a human to do this, that's too much, and the data will increase. So when we have this kind of problem, like a big data problem, people tend to go back to the statistical machine learning. But because of the things I explained before, statistical machine learning does not help in this kind of problem that much. So one way, my previous way of solving this problem was, oh, this is so easy for human. So how about put human in the loop and amplify? Human has a problem in the scale up, right? So how we can scale up human's ability to handle this task? So it's like maximizing human's ability. I call it visual analytics, and it's like not competing human and machine. We are not competing, and we are working together to make things better. So basically, we first understand what is the machine output and tries to steer the algorithm. So this kind of thing is what I have done during my PhD, and Paul is still doing one project like that. However, there are limitations in visual analytics method too. It is not still perfect. No, not at all. So the first problem is the visual analytics approach is application domain specific, meaning you have to build a new tool for a new problem. You cannot use the same tool and let the tool do many things. And it's limited by the underlying models. For project Paul is doing, is relying on the first approach. And as I said before, you cannot differentiate this kind of simple semantics. So there are limitations. We can go with this. So while I was doing my PhD, when I built some visual analytics tool, I wanted to use this tool to find some interesting pattern or insight from the text. Let's say it's comments from the New York Times, and it was actually very time consuming to find something that is non-trivial and something I didn't know before, something that is surprising but still meaningful. I have to explore the data hours and hours, but it's still difficult to find it because many signals are lost in the bag-of-words model already. So only a very strong topical signal survives. Very apparent, very something that is very strong survives. And we humans are lazy and we do not want to explore the data and do the hard work, right? It will be better if the machine can do things. So how we can approach this? So we can say in our lab, our first goal is solving open-ended task. This is our goal, right? And open-ended task is something that is very easy for humans, very difficult for the machines. So the first approach was maximizing humans. So that was the visual analytics approach. However, as I said before, there are some limitations we can go. So my next approach that we are pursuing in this lab is, can we simulate human? Can we build something like a human? And have you guys watched this movie? It's a new series of the Alien. I highly recommend you guys to watch this movie. I should say this is a required movie for the So this is the second episode. So he is targeting trilogy. You have to watch the first one and to see the second one. So this is the second one, and the third one is not yet ready.
So is it in Netflix? Where is it?
It is not in the Netflix. Maybe you have to go to the Redbox or something like that. Yeah, and try buy somewhere in the. Maybe I can invite you guys buy the Google Play, buy it on the Google Play, or buy a DVD and play it on the lab together. I think that will be a better idea. So let me buy the this for educational purpose. Okay. So let's continue. By the way, let's see.
Introducing the next generation David. Launching June 8th on the Prometheus.
This is
What is it
video, not
about
the movie.
robots that makes them so robotic? At Wayland Industries, it has long been our goal to create artificial intelligence almost indistinguishable from mankind itself. Hello, I'm David.
What can you do, David?
I can do almost anything that could possibly be asked of me. I can assist your employees. I can make your organization more efficient. I can carry out directives that my human counterparts might find distressing or unethical. I can blend in with your workforce effortlessly.
David, what do you think about?
I think about anything. Children play, angels, the universe, robots.
David, what makes you sad?
War, poverty, cruelty, unnecessary violence. I understand human emotions, although I do not feel them myself. This allows me to be more efficient and capable, and makes it easier for my human counterparts to interact with.
Is there anything you would like to say, David?
I would like to express gratitude to those who created me. Happy birthday, David. From Wayland Industries. Eighth generation Wayland type. Technological, intellectual, physical, emotional.
Okay, so even if you guys didn't see this movie, you can see it's like AI or droid that you guys are familiar with. There are many things like him in the movies, so it's very easy to imagine. So what if we have something like that, then it will overcome this limitation. It will be very general. It will do this. It can solve this problem, this problem, this problem. And it is not limited by the underlying models like that. And it does not require human effort. So, this is what when layperson, not the computer science major, say AI, and that's what they imagine. And our biggest secret to them is that we do not study things like that. So it's a best kept secret. When we say AI, we don't mean things like that. So we can see if we compare the 1930s physicists, there was many experimental physicists who did many interesting experiments. So there are multiple complex experiment results. And there are some theoretical physicists who provide underlying theory behind. So if you use this theory, you can solve many problems. You can explain many experiment results, things like that. So that's what they call theoretical physics. And if we compare them and us, we can see there are many people who are producing interesting multiple application-specific models. And we need somehow a model that can do many things. So we need some theory about how we can combine these models like image capture model, self-driving model, drone model, or language machine translation model, things like that. There are many models that is application specific. And the difference between the those application specific model and the AI model in the movies is that they can do many things. So originally, when they they say AI started around the 1950s, and there are many at the time, how I say, world's top scientists, best scientists gathered at the some conference and Dartmouth College, and let's solve this problem together. And that's when they coined the term like artificial intelligence. That was the model like David was what they wanted to do. However, as you guys know, there were many failures with that. So I will briefly say there was more than 2 or 3 AI winter during the history. So let's see. So when people wanted to build a multiple model that can do many things, they quickly failed. It was too difficult. So they say, okay, and they at first begin with a symbolic AI, right? So they have some rules, and if they have a knowledge database like this, then they can use these rules to calculate the answers, right? That was their approach. It is like if traffic signal is red, stop, else cross the street, things like that. So this was a rule-based approach, but they quickly found that it was actually very difficult to, how I say, build actual artificial intelligence. One reason was things like this. If traffic signal is, then the first problem they met was that it is actually, if you build a robot, it is very difficult to find what is a traffic signal from its camera. because the traffic signal, if you think about the traffic signal, there are many different shapes of the traffic signal, and even for the same traffic signal, it changes its pixels based on its angle or lighting, time of the day, is it raining or something like that. So some philosophers might say there is no same traffic signal in the world, right? It's like if the river flows, there is no same water again. So that was the first problem. And then the second problem was, okay, if it is red, then you stop, but if not, then you cross. But what if the signal is broken? So there is it is just blinking randomly. Or you are crossing the street, and you are almost there. You have just one more step left, but the traffic signal turns into the red. Then you stop there in the middle of the road, right? Then you should say, oh, by the way, if you how else if you are in the middle of the road, stop. Oh no, do not stop. Hurry, actually. Things like that. So the condition goes on. Let's say there was some, how I say, blackout. Then what should we do then? Things like that. So this if or rule-based rule quickly failed. The next thing came the what you guys think neural net. The connectionist AI. They call it a connectionist AI. It's what you think of nowadays neural net. But they also failed. Actually, they failed a few times, but let's say they failed. So the situation was like if you put neural net in the grant proposal, then you cannot get funding. They does not even read. They just do not give you any funding at all. And so people created a term like a machine learning, right? To differentiate, to change the name. And besides the name, the focus slightly begin to change from the general to application specific, because building a general AI was too difficult, so they slightly let's solve this simple problem first and extend. And machine learning was a little be successful, and the deep learning was much more successful. And nowadays, then suddenly there is it began with a journalist. Journalists come to you and, oh, you build an AI better than human, right? For image classification, things like that. Then researchers say, oh, no, this is not AI, this is not closed AI, but then the investor comes, and if you do research AI, I'll give you lots of money. Then okay, whatever, we are doing AI, so give me the money. So things like that happen. So nowadays people say AI, and most of the AI is, by the way, application specific. So original people who wanted to build something like the Android, if they say, oh, I study AI, then it is actually very difficult to explain what you do nowadays. So actually this is very common, very interesting thing. If you build a very successful thing in AI, in computer science, the word loses meaning. So the similar thing happened in HCI. So nowadays, if I go somewhere and say to people, I study HCI, then the people does not know what I do. It can do lots of different things. And the same thing with AI. So if you go to the mechanical department, environment department, biology department, economy department, they say they are doing AI, things like that. Basically, they are doing machine learning, but they say, oh, we are doing AI. So we need some different term, right, about to describe things like David. So, and because it has a more than 60 years history, there are lots of names. Names like strong AI. Yeah, HDI is one of them, and true AI, and human-like AI, or there is even term like good old-fashioned AI, GoPy. So this term is actually on a book that is written by the University of Toronto professor of emeritus of computer science who studied. Pardon me?
Is it Hinton?
No, he is actually he is the one who created the Winograd test. It's Lebanon, something like that. So okay. So even funny names like good old-fashioned AI. So, however, these are all a little blurry. A strong AI or true AI looks like, oh, I'm real, or believe me, or something like that. So, however, artificial general intelligence is what the term I would like to use in general, because it catches the essence of what we are trying to do. We are trying to build an AI that can do many things at the same time, while the most of the AI nowadays is application-specific AI, right? So that is the big direction. Then the questions might arise. Hey, professor, why multitask is different, right? Because we have a model that can do 3 things. Then why just we build some model that can do 3 things at the same time? Let's build a model and apply the same data set and train it like this, right? So why there are no papers that there are no models that does the machine translation and self-driving and image generation, even though there are models that does one.
Because the different data set,
Mm-hmm.
they have like different distribution, distribution. So if you train, even for the machine translation also, if you choose one algorithm,
Mm-hmm.
and if you train on the data set, so that algorithm is not good for the different data set.
Mm-hmm.
So these are like mostly specific with the particular data set. One algo is better on this data set and it may not perform well on another. So every task has their specific requirement.
No.
I think it's because the problem is when to use.
Mm-hmm.
When to use, like suppose you train in the AI, you have
Mm-hmm.
you have trained for all 3.
Mm-hmm.
The question comes when, how do you decide, how does the model decide when to use which model, which approach?
Mm-hmm. That's an interesting aspect. Sanjay?
It comes back to the same context,
Mm-hmm.
what he's saying, in what context you use which one.
Mm-hmm. By the way, there are no ground truth answer for this. So what is important is you guys think about why multitask is difficult. And I think it's 2 p.m. So we will continue next week. So you guys have 1 week to think about, hey, professor, I build a model that can do 2 or 3 things. You are wrong. So think about why it will be difficult. And we will continue there, okay? And Sanas, would you